Robots performing tiring and laborious tasks in isolated work cells are a common sight on factory floors. In recent years, however, there have been substantial efforts aimed at altering the landscape of traditional automation by providing access to robots that are safe for human interaction. Such human-safe robots could perform tasks in direct contact with human co-workers without risking injury. Researchers around the world have been working to address a number of technological challenges. One group in particular that has made significant progress in this direction is led by Dr. Kermani at Western University.
The focus of our research is on the development of a new type of robot that can safely and intuitively interact with humans. And that's different from what currently being practiced in industrial applications in that there's almost no interaction between humans and robots, unless through some sort of programming and coding. Now the challenge is that as soon as we try to make a robot safer or more human compatible, then immediately the performance of the robot starts to degrade. Now to address this problem and solve it, we really had to disconnect ourselves from traditional design practices. We developed a new type of actuator that would allow us to achieve both objectives, performance and safety. In this actuator we used a special type of material called magnetorological fluid, which essentially is a fluid that can change its viscosity in response to magnetic fields. Now we use this fluid to power to the robot as it needed when it needed. In that case, the robot has no excessive torque or force to harm humans, and at the same time, it has enough power to do its job.
My name is Alex Schaefer, and I work on advanced actuation techniques for human-safe robot interaction. The distributed active semi-active actuation approach uses a single motor to drive multiple joints of the robot simultaneously. The motor drives a set of gears which produce rotation in both clockwise and counterclockwise directions. The mechanical motion is transferred to the joints using a system of belts. Each joint is driven by a pair of magnetorheological clutches. The clutches are driven in opposite directions, which creates an antagonistic behavior. In this way, we can drive both clockwise and counterclockwise torque to each of the joints independently and simultaneously without changing the speed or direction of the motor. This arrangement allows us to locate the motor at the base of the robot, which reduces the flying weight of the robotic arm. The DASA configuration with antagonistic magnetorheological clutches allows us to achieve performance levels not attainable by conventional servo motors. The actuation is completely compliant, making it safe for human-robot interaction.
We not only make the robot safer because there's no excess power in the robot, but at the same time we can maintain the performance of the robot. So we can create that balance between performance and safety.
With this actuation, we transfer power from motor through some gearbox and a set of pulleys and belts to the first joint, and then we transfer the power from first joint to second joint. With that, we can have fully actuated robots, and interaction can be done through this actuation.
My job is designing an FPGA circuit board which can be integrated into our MR clutch. With this board, we can control the output torque of the MR clutch and make it as a linear actuation.
In this lab, we work on safety in human-robot interaction, and essentially my project involves detection of collisions without using tactile sensors. What we're looking to see is if an interaction between a robot and a human is an intentional interaction where the human is trying to teach the robot something, or when the human is accidentally had an impact with the robot, and how the robot is supposed to react to these different scenarios.
This is an example of our actuation approach, which uses a single magnetorheological clutch to drive a robotic arm. The transmission torque is controlled by varying the magnetic field inside the clutch. Tiny sensors embedded inside the design of the clutch allow us to measure the intensity of the magnetic field. By using feedback from these sensors, we're able to achieve closed-loop torque control without the use of costly torque sensors. Torque control is essential in human-safe applications as well as numerous other robotic and industrial applications.
As the technology for this actuator matures, we find applications in which we can either significantly improve the state of the art or even start to think about doing things that were not possible in the past. An example of which are new methods of transportation, teleoperations where two robots are remotely connected and have more human-like behavior, food and entertainment, and agriculture.
As an emerging topic in robotics, human-safe robots are expected to greatly affect the future of this field. Designing robots that are safe is not merely an ethical issue. Rather, the economic impacts of safe and dependable robots in manufacturing are tremendous. Research and development conducted by Dr. Kermani and his team for the development of an actuation solution that provides a pragmatic balance between safety, performance and cost is a significant step towards realizing the next generation of human-safe robots.